Okay, in this section, I want to look at being able to draw shear and moment diagrams, knowing the relationships that we found with integration, knowing how we find slopes and everything. How can we do this without a lot of calculations and some things just by observance, right? So if the shear and moment as a function of position of x are known, then drawing shear and moment diagrams is straightforward, and we just did that. But if all we're looking for is the shear and moment diagrams that are desired and trying to find the maximum values, then we don't have to use those other methods. There's other ways of drawing these diagrams that can be very useful. And one of the things, of course, is, again, knowing the slope information that we covered last time. That is extremely important, and we'll see how that can be used. Okay, in your book on page 517 are a number of tips for drawing shear and moment diagrams, and I'm going to run through some of these. They're kind of rules for drawing shear and moment diagrams, and these should kind of help you. So the first thing is, in regions of a beam where the distributed force is 0, the shear is constant and the moment is linear. So in this first example for this particular one, it's saying we just have one load. We know that our shear diagram will look something like this. It will go down and stay constant at some negative value. Our moment diagram, this is our moment, will be then linear. Okay? So again, there's nothing for a distributed load, so our distributed load is 0. Our shear is constant at some v, and then our moment is linear. So you see how that always goes up. In regions where we have a distributed force and it is a constant or uniform, as in this case here, we see that the shear is linear and the quadratic is, and the moment is quadratic, So let's look at that. If I draw a shear and moment diagram for something like this, it is again saying that my shear will be linear and my moment will be quadratic. And we know this based off of the method of integration, right? This is to a power of 1. This is the power of 2. This is the power of 0, power of 1, power of 2. And then likewise in this last example, if it is linear, right, going across, we then know our shear. This is our shear moment, that our shear diagram will be quadratic and our moment will be cubic. Okay. The next rule we have is that at point A is an unsupported end, so like a cantilever beam, with no concentrated force and no applied moment, as shown in this example. You can have a distributed load on it, and at that location, we know the shear and the moment both will be equal to 0. Okay, if I take a small slice here, infinitesimally small, our shear will be 0 and our moment will be 0. If we continue along this example of a beam in X as we go across, we see at point B a distributed force ends. The shear and moment diagram to the right of B is the same as those to the left. So the value at either side will remain the same. If we continue on along, we see C. We have a shear to the right of point C is lower by the amount of F sub C. So there's a jump in our shear diagram. It will jump down in the direction. It will go in the direction of that load. And the moment to the right and the left remains unchanged. Continuing across, the shear at D to the right of D, we know we'll have some reaction force at D, will be higher by the value of this dy. It will jump up at that location. And then again, the moment will be the same on either side. Last, a concentrated moment of ME acting counterclockwise is applied at E. And the shear at the right of E is the same. So the shear itself does not change, but the moment will. The moment at the right of E will be lower than the moment to the left by the amount of M sub E. This last one can sometimes be a little confusing, this moment one. One way I like to look at it is if I redraw this moment on here, if I have this beam again, like this, and let's just say I have a concentrated moment on there, such as that one, I like to draw it either like this, as it's shown this way, and then when I draw my shear and moment diagram, while it is a positive moment, let's say I have some moment going along, maybe it's linear for some reason, this will jump down. So a clockwise will make it jump down or go lower by that amount, and then it may continue. This value is M sub E. I like to draw it this way to show the direction that it's going. It's going to be jumping down. Likewise, if I had a negative moment applied, I would draw it like this, and then that will tell me that it will jump up. So let's take a look at one example. We have this example where we have a shear and moment diagram for beam ABC. We see it's simply supported with an overhang from B to C, and we are to draw the shear and moment diagram. It is not asking for any equations or anything like that for the shear and moment, just what the diagrams are. Normally I would draw these diagrams underneath, which is the proper way, but it's lined up this way, so we're going to leave it this way for now. So the first thing we need to do is we need to determine the shear and moment diagram looking at a few locations of the beam to obtain some data points. The first thing we need to do is find our reaction forces. And I'm not going to go through the methods of that. I will just kind of put those on there for us. Okay, so after we find the support reactions, we can start drawing our shear diagram. The first thing we know is that we have a positive 10 going up, so our shear diagram will start at 10. We know as we go along in 16, because this is constant, it will be a linear decline. It's a negative 2 will be the slope. Remember, dv dx is equal to a minus of the w. So in our case, it's going to be constant, which is going to be a minus 2 is our slope. And at 16 meters, we will be to some value. So we don't know what that value is, but if I take my 10 and subtract the area under this part of the curve for us, right, that is 2 times 16, which is 32, which takes us to a negative 22. So it will be a linear slope going down to a negative 22. And then we see we have a positive jump of 30 going back up, which takes us to 8. It tells us the direction that we're going in. And then the last, there is no shear at the end of an overhang. That better come down to 0. So if we take the remaining area on this side over here, we have 4 times 2 is 8. So that does bring us back down to 0. So there's a quick, easy way to find our shear diagram. Now let's take a look at our moment diagram. We know in the beginning our moment should be 0 with a pin. We know that that should be there. We know that our moment diagram will have a positive 10 slope based off of this value of the shear. Remember, our slope is dm dx is equal to the value of shear at that location. So it is going to be going up, and it's going to be some cubic amount, or quadratic, because this is linear. Okay, so we know, one thing we know is that this slope is going down as a negative 2, and we want to find this location where it's crossing because that's going to be a min or max for us. And also we see that on either side our slope changes, right? So we start out at 10, it goes down to essentially 0 for our moment, and then it continues on up to a negative 22. That location, if we want to find that, we're starting it out at 10. It will go down to 0 by 2, so it's going to be equal to x, or x equals 5. So 5 is where this thing will cross or peak for us. That max value is, again, the area under this part of the curve, 10. So the value will be 10. 1/2 base times height times 5 divided by 2 should equal 25. So it's going to go up to a value of 25, and then it's going to come down. Okay, so again, we're up here at 25, and then we want to know what our new value is. So we're going to be subtracting this area here to find our next location. That area is, again, this is 5. 5 to 16, that is 11 is our base. Our new value is 22 divided, divided by 2 equals 121. So we're going to be subtracting 121 from this. We'll have minus 121, and then adding our 25 to it, which is this value here, gets us to a negative 96. So we're going to be going down to a negative 96 at some point here along 16. So this will continue on down to a negative 96. And last, we see that our curve will come up this last little bit here, starting with a positive slope going in that direction. This area here is 4 times 8 divided by 2 is equal to 16, a positive 16. So our curve will go to a negative 80. And then jump back up. So let's look at a few things real quickly. Our slope again, the slope here, starting out is a positive 10 is our slope. It ends up at 0 because it's crossing the x-axis at that location. Down here, it is a negative 22. And on this side here, it's going to be this positive 8. And it will end up at 0 for our slope. Over here, we see it's constant all the way through, no matter what, on all of these, of a negative 2 based off of, based off of our distributed load. So our dv dx is equal to a negative 2. So this is negative 2, and that slope is negative 2. So there we go. That's one way to solve this without having to draw or calculate any of the equations for the shear or moment diagram.